Right now, artificial intelligence research is accelerating under its own momentum, pushing technological capabilities into entirely unmapped strategic territory. This graph maps expert predictions for high-level machine intelligence. Between 2022 and 2023, the median estimate among surveyed AI researchers moved sharply backward, dropping from the year 2060 down to 2047. That is a 13-year jump. Looking at this same timeline, prediction markets and compute-centric models pull central estimates even closer, clustering tightly in the early 2030s. We are seeing this timeline compression happen simultaneously across multiple independent analytical vectors. This is occurring even though the forecasting methodologies themselves, from crowd platforms to hardware trend extrapolation, are still in their infancy. Decision-makers now face a unified directional signal toward near-term artificial general intelligence, turning a theoretical debate into an immediate strategic mandate. Yet, if you look closely at the people building these systems, a paradox emerges. Top researchers are looking at the exact same data and the exact same scaling laws, yet reach sharply different conclusions on the arrival date. Anthropic CEO Dario Amodei projects that AI systems operating at a Nobel laureate level could emerge in just 1 to 2 years. Conversely, Yann, LeCun, Meta's chief AI scientist and a Turing Award winner, insists that achieving true human-level intelligence will take a decade or more. This immense variance is not random statistical noise. It is the result of a structural disagreement built on 3 hidden variables that drive every prediction model. To build actionable strategy under this level of uncertainty, we have to deconstruct the architecture of an AGI forecast. We need to isolate those 3 variables: definitions, methodologies, and cruxes. The first variable is the definitional mismatch. When timelines clash, forecasters are often predicting entirely different nodes in the technology lifecycle. This diagram breaks down the 3 distinct stages of AGI rollout. The first node is capability existence. This is the exact moment an AI system achieves a specific intelligence threshold within a closed internal laboratory environment. The second node is operational deployment. This represents the period when that laboratory capability is taken out of testing and integrated into widely used commercial products and enterprise workflows. Once deployed, massive consumer user bases can adopt these models with staggering speed. ChatGPT, for example, reached 100 million users in mere months. Returning to the flowchart, the final node is societal transformation onset. This is the point where the deployed AI measurably impacts macroeconomic growth, automates broad swaths of labor, or shifts geopolitical dynamics. Historically, the gap between the invention of a general-purpose technology and its macroeconomic impact spans decades. But software distributes globally via cloud infrastructure almost instantly, and an AI system capable of recursive self-improvement could drastically compress this historical timeline. A computer scientist predicting 2030 for capability existence and an economist predicting 2045 for economic transformation are actually in complete agreement. They are simply measuring different nodes on the timeline. The second variable driving the disagreement is methodological limits. Institutions rely on 4 distinct data-driven methods to predict AGI arrival, and each carries structural flaws. The first method, expert surveys, suffers from a well-documented phenomenon known as moving horizon bias. This is the human psychological tendency to consistently place complex technology a comfortable 15 to 25 years in the future, regardless of when the question is asked. Next are prediction markets. These platforms react faster to fresh information, but struggle with long horizon questions. Because AGI is a semantic concept, markets must use narrow, verifiable resolution criteria, which often sets a lower bar and artificially shortens the predicted timeline. This chart visualizes the third method, compute-centric models. These project timelines mechanistically by calculating exactly when available processing power, measured in floating-point operations, will scale up to match estimates of human brain computational capacity. Finally, we have empirical trend extrapolation. This graph highlights Metra's approach, tracking the 50% task completion time horizon, a metric observing the shrinking amount of time it takes for an AI agent to successfully execute long, autonomous software engineering tasks. This expansion leads toward the AI R&D automation feedback loop, a scenario where AI begins to assist in its own development. This diagram maps the dynamic. As AI partially substitutes for human engineers and researchers, it drives down compute costs, discovers architectural improvements, and mathematically accelerates its own evolutionary cycle. Once that loop engages, the transitional jump from human-level competence to superhuman systems may happen within a window of just a few years.
Because all four of these forecasting architectures are nascent and lack rigorous adversarial validation, the exact dates they output are highly uncertain.
The specific year matters far less than understanding the underlying acceleration mechanics they reveal. The final variable is the capability crux. This is the core epistemological divide over how artificial intelligence actually learns and generalizes to novel problems. This chart illustrates the two primary camps. Path A represents the scaling maximalists. This group operates on the premise that simply feeding exponentially more compute and data into existing deep learning architectures is sufficient to achieve general intelligence. They argue that historical scaling laws have held true across multiple orders of magnitude without fail. If high-quality human text runs out, they believe synthetic data will seamlessly solve the bottleneck. Path B represents the architectural skeptics. This group argues that current autoregressive models face a hard, insurmountable ceiling, regardless of scale. This is grounded in the stochastic parrot critique, the theory that fluent statistical pattern matching over massive datasets does not equal causal understanding. Under this view, language models lack a true, functional model of the physical world. Furthermore, researchers estimate that the available stock of high-quality human-generated training data will be completely exhausted between 2026 and 2032. This variable provides the mathematical weight that swings a forecast from 2027 to 2040. If the maximalists are right, the timeline to AGI is immediate and bound by hardware construction. If the skeptics are right, a human-driven conceptual leap in architecture is required. We are already seeing human-AI collaboration frameworks attempting to bridge these exact capability gaps in complex, iterative reasoning tasks. Ultimately, an expert's forecast for when AGI arrives is inextricably tied to how they believe the system must be built. Beyond the academic debates, there is a final metric, the market weight signal. Here, massive capital expenditure acts as an implicit, revealed forecast. Major technology firms are allocating over $300 billion annually toward AI infrastructure. To put that in perspective, the largest previous AI boom in the 1980s saw total project funding of roughly $500 million over a decade. This scale of investment requires absolute skin in the game. It suggests internal corporate timelines among hyperscalers are aggressively short, backed by extreme financial confidence. However, this immense spending might also be driven by competitive panic. For these firms, the geopolitical and corporate cost of falling behind in a potential winner-takes-all scenario is total obsolescence. While these corporate timelines may be partially inflated by market dynamics, the sheer volume of capital guarantees one thing: the attempt to scale to AGI will be relentlessly and fully funded. This leaves policymakers with a severe dilemma. How do you properly govern, regulate, and secure national infrastructure when credible scientific predictions for transformative AI range anywhere from 1 to 20 years? The primary fallacy is optimizing national or corporate strategy around a single point estimate. Structuring a security posture around the year 2047 is mathematically and strategically dangerous if the breakthrough happens in 2028. Planners must abandon debating exact calendar dates. Instead, the strategic priority is building adaptive capacity. Adaptive capacity ties strategic actions to real-world capability triggers, not chronological deadlines. For example, organizations might monitor the percentage of AI R&D tasks successfully automated by AI. If systems autonomously execute multi-week software projects, a pre-planned policy for extreme timeline compression is triggered. Forecasting serves to construct the bounding boxes for scenario planning, identifying the limits of what is plausible. Preparation is paramount. Waiting for absolute consensus guarantees failure. Decisive action based on capability triggers ensures readiness, regardless of the ultimate timeline.